we will explore one-hot encoding and what it actually means and how can that be useful. And then from that, we will build a way of parsing a full data frame and create a one-hot encoding version of that. One of the things of what hot encoding is that it will create a very sparse vector representation of your data set. So you might want to do some dimensional reduction after, and then that's when we do the hashing. So we'll get into more detail for each one of those cases. But the idea will be to, yes, do a prediction of the click-through rate. So you have a set of features. We're not interested necessarily in what those features mean for this particular lab, but more importantly, how do we work about it by doing some sort of encoding of those features. So I found this very good explanation of what one example of what one hot encoding means. So let's assume that you have 7 rows. So you have some data that contains 7 rows, and then there are different categories, and then you could encode those categories with a number. So that number being let's say 1, 2, 3, and 4, given that there are only 4 categories. But if you do that somewhat, and then you try to use that into an algorithm, this numerical encoding somehow would give you some set of ordering. And in this particular case, this categorical, this particular type of category variable, this category variable really doesn't contain ordering. So there might be some other way that we can encode that information so we can pass to an algorithm. So that is what one hot encoding does. So in a way, for each one of the categories, it would have only 2 values, 1 or 0. And it will be 1 in the cases for which that category is present, and 0 otherwise. So the first one, the first row contains 1 in the column human, and everything else will be 0. And then similar for all the other columns. So if you notice, there are a lot of zeros, and that's the representation in a way, or that representation is very sparse. Imagine when you have, like in this case, you have thousands of unique categories, or in the case of the full data set, of the order of millions. So that might not be ideal. So in that case, what you can do is take that vector representation and then find a reduction. So that's when you do, one of the techniques to do that is to do hashing. So what does it say here? This works very well with most machine learning algorithms. Some algorithms like random forest handle categorical variables natively, so you don't necessarily have to do that. But yeah, so one note here, modern machine learning libraries take care of it. So in the case of MLlib, we saw that there is already a functionality to build this sort of encoding without you having to actually write all the encoding. So let's get back to the lab. And so the very first, yeah, here. So we have 3 samples. So we have 3 samples, sample 1, 2, and 3, and each one would contain data points. And so in the first, let's see, representing, each one of them representing an animal. So the first feature indicates the type of animal, the second, the color, and the third describes what that animal eats. So if we look at that particular data set, we see that this is the sort of, so the mouse is of color black, the cat is tabby, and the bear is black. And what do they eat? So that is one way of representing this data set. And we can build a data frame from that. So that is what we're doing here. So we take each one of the samples, and we say that those samples, we send them into a into a column called features, and that's what that's what we show in this case for the second data frame. I think at this point you guys are very familiar with creating data frames. So unless you have some question, I'm going to go to the next section. The next is, well, we could do this sort of encoding in a manual way. So notice that in this case, for instance, we have mouse on the column food, but as well in the column animal. So in a way, if mouse is in the column, in the first column, is different as if the mouse is in the third column. So we have to find a way to encode that. So in a way, the very easiest way would be to encode each one of the unique tuples. So remember that the first element represents the column number, and then the second one, the value. Would be to then encode each one of them with a different value. So we would have 0, 1, 2, 3, 4, 5, 6. So in a way, that is our manual way of doing this encoding. So in this case, we have, for the example of the mouse, we have 2 and 5, which still is mouse, but we know that they're in different columns. Any question here? No questions. That's good. Then we go into sparse vectors. So somewhat what we saw in this example, right? We're going to create this sparse representation. Or if you have this sparse vector, there are a few ways of representing this data. One way, for instance, could be saying what are the columns that have a value different than 0 and only present the information there. And you could do it either by presenting the values, sorry, the indexes in one array and the values in another array. And then, of course, these two arrays would have to have the same size. Or you could have a list of tuples where the first element of the tuple is the index, so the column number and the value. And that's what we see here with this sparse vector. So you could do 2 representations. So this is the first representation. So this is the size of the vector. So in this case, size 5. And then we're saying which ones are the indexes that are non-zeros. And then what are the values for those non-zero values. So we're saying the first, third, and fourth index are non-zeros, and everything else will be 0. So that is the representation of this one vector here. But you could in principle represent similarly. You could represent, and that's one way of representing, but you can also do it in the following way by saying you have an element, a vector of size 5, for which the third element is a 1, and the first element is a 2, and that is what this vector here would look like. So let me just make this a little bit bigger. Okay. And those two types of representation are available in the Spark ML library under sparse vector. And so the purpose of this is to show that if you do an operation in a sparse vector and a regular vector, so a dense vector, in this particular case, the dense vector would contain the value for each one of the elements, while the sparse representation only contains the values for those non-zero elements. And when we do the dot product between this sort of reference vector W and the dense and the sparse representation of A, we should be getting the same value. And that's what we see here. Any questions related to sparse vector?
Hi, I have a question.
Yes.
When you import PySpark ML linalg, if I use MLlib, does that affect the result?
No, it should give you actually the same. We could try it out, but then In this case, no.
Okay.
But then what happens? But that is not the supported library, right? So that is in what's it called, maintenance mode. While the current library is the one that so we do MLlib.
Armando,
Yeah.
just to clarify,
Yeah.
just to clarify the difference between ML and MLlib.
Yeah.
MLlib is the original Spark machine learning library that started at Spark 08, and it is based on RDDs.
Mm-hmm. Yeah.
The ML is a machine learning library, a newer machine learning library that was introduced in Spark 1.4, and it is based on data frames. Both MLib and ML have an object called sparse vector, but those are two different objects.
Mm-hmm.
So if you're using an ML algorithm, you need to use an ML sparse vector. If you use an MLib algorithm, you need to use an MLib sparse vector. So that's just so people are aware that those two libraries, although the name seems the same, they're under the hood, there is a great deal of difference.
Yes. Yes, exactly. And the reason why we're using the ML and not the MLlib is, as Eyal mentioned, this one ML is based on data frames, and that's what we are going. So the algorithms that we're going to be calling the logistic regression are based or are coming from the ML library. So if you were to go here to the programming guide, MLlib machine learning. So this is the RDD base, and that is MLlib, and this one is ML, although the name is still MLlib. But this one is, yeah. So why I put only the one for ML is because that is the one going forward, the one that is going to continue being developed. Okay, but the result should be the same. Like if you were to call this with either one of those, the result of this particular dot product is identical. But yeah, the underline very different. Okay, good. Thank you. So now that we know we can represent this one hot encoding features for a sample data set, let's try using the mapping so that we define in the part 1A, this manual one hot encoding for sample data points. So in this case, we have, these are the features that we have, right? I remember that what we're going to do is every time the tuple 0 and bear is present, our encoding will be a 0. Every time 0 and cat is present, our encoding will be 1, and so on until number 6. And so if we have 3 samples, the samples that are here, the first sample, right, would be represented by the second tuple, oh, sorry, the second element, or the number 2, so that encoding, and one black would be 3, right? So what this says is that column 2 would have a 1, and column 3 would have a 1. And everything else will be a 0. Yes, so and that's exactly what we have here. We're saying that the dimension of this particular sparse vector is 7, and 7 in this case would be the number of features, the number of columns that we have here, so the number of features. So in this case, 7. And we're saying that number 2 would have a 1, so that corresponds to this one, and number 3 will have a 1 that would correspond to this one here. Any questions there? No questions, good. So now we'll use this one hot encoding dictionary that we got from 1A to generate the features from the original categorical data. So the idea would be, let me see, make sure that I follow. This is 1D. Okay. So the input for this function is a list of tuples that would have an integer and a string. And the returns are a sparse vector of length and number of features with indices equal to the unique identifiers for the tuple that occur in the observation with values equal to 1. So we're trying to write a function that would automatically would create this sparse vector from the input. Given that we already know the dictionary that would create these mappings. So in this case, that's exactly what we're doing. The number of features, that is, in this case, would be 7, right? Or you could also alternatively just calculate the length of that dictionary. And then the sparse vector, the vector, in this case, would be the value of the tuple and the number 1 for each one of the elements of the row features. This list comprehension might be confusing, but I hope the meaning is clear. So what we're trying to build is this representation, right? So that would be, if you see, we have a sparse vector, and here we have also a sparse vector, and this is what we're constructing. Right? We're constructing a 1 where the feature and value, which are the keys for this dictionary, yes, this is the key for this dictionary. The value of that, whenever that is a 1, that's when that's what we set equal to 1. And so the example is, if we take sample 1, which is sample 1, where's that one? This one here, now it's in black. We know that the encoding representation is that the second index is equal to 1 and the third index is equal to 1, and all the others would be 0. And in fact, that's what we see here. The 2 and 3 are the only one non-zeros, and their value is 1. Any question there? There's the other, since in this particular case, we're using this dictionary. This dictionary is going to be used every time we do the encoding. Would be a good idea, especially if this dictionary is small, to broadcast that variable so it would be available for each one of the executors instead of having to copy that instead of having to copy that every time the function is called. That function would be available just for each one of the executors. So that is the purpose of this broadcast that we already saw in the previous sessions. Okay.
Hey, Amanda, I got a question.
Yes.
Because in the one hot encoding function, you set value as 1, and 1 is an integer. How do you automatically turn to a float? Like at the end is 1.0.
Yeah, you're right. Let me see. Right here, I'm saying it to 1. Sparse vector. Let me just look at something here in the documentation. Right. Right. Okay. Right. So this is what's happening. So this is the sparse system. So it takes the indexes, the rate of the indexes, and the values, which are double. So I think here's where the conversion occurs.
Okay, thank you.
Okay. Okay. So now we did the operation on an element per element, but of course, if we have a data frame, which is what we're going to be working with, we like to be able to create that the same sort of encoding for the data set. And of course, this is a sort of toy data set, but at some point when we load the data, we want to make sure that we can apply this one-hot encoding to the data frame. So that's why we will need to generate this user-defined function that that can be used on the data frame. And just let me make sure that I follow here in the other notebook. Right. Okay. So in this case, what we will be doing would be to take a one-hot dictionary, right? We'll reuse this function to generate the UDF that can be one-hot encoded row based on the dictionary built on the training data. And it will return the user-defined function. All right. So the length, and why do we need, why in this case we need the length, is because the one-hot encoding function would take the value, right? Would be the value x, the value which in this case is this x from the lambda function. The second parameter is the dictionary, which is passed here, the one having the dictionary that would contain the keys or the unique values, and then the length. And why is that? Because that is what this function is expecting, right? This function expects the row features, the dictionary, and the number of features. And that's what we pass here. And so if we then call the function, we call the function into the sample one-hot encoding dictionary. So this is a data frame. Let's just look at it so we know exactly what's happening at cell above. So we do display of this. Oops. Oh, because this is a dictionary, yeah. Yeah, how do we get the value of this? Wow, yeah. Yeah. So that is, oh, yes, that is the dictionary. And this, right, and then so if we look at this one, what does it have? This one. This is the UDF. And that's the UDF that we're going to pass to the data frame, right? So in this case, the data frame is this one here. And right, the data frame that we built in the very beginning. And what we're passing is the column features, right? Which is actually the only column that that data frame would have. and we are applying that UDF. And then the result of that would be the one hot encoding representation of that data frame, right? So notice that we went from this representation to this sort of more compact representation. And then the key to go from one to the other is that dictionary, that encoding that we saw, right? Which was I don't want to sell above, would be this value. Well, oh no, this is the one for the full data set. What did I do? Oh, the sample. Yeah, that is for the full data set. We don't want to go. Oops. Okay, right. So this is the key that will allow you to do the mapping from this representation into this sparse representation. Any questions until here? No questions, good. All right. So what is next? The next thing is to construct the one hot encoding dictionary. So we already have the data frame, create a data frame of distinct feature IDs and categories. In our sample data set, we had 7 items. And why is that? Is, I mean, if you think about the number of items in that particular data set, for instance, this black appears twice. So you in a way would save the space of representing this. How to explain that? In a way, you are encoding this that appears 2 times into one column only, instead of if you this only represents the unique values of that of each one of the values presented in the data set.
Armando?
Yes.
There is, I think, only one blank value in this. We have written like twice.
Yeah.
Blank appears twice, but I think there is only one blank, right?
No, here 1 and 2. What do you mean? Sorry.
Oh, black. It is black. Okay. Oh, I thought it is blank. Okay. Sorry. That is my mistake.
Okay. Okay. So if we want to first find out what are the values that would appear into all the features, what we do is we call explode. So what does explode do? So we can, no, this will not be here. Oh, I think, yeah, here is a link to it. So we'd create for each one of the elements, for each one, returns a new row for each element in the given array or map. And that's exactly what we want to do here. We want to take for each one of the elements of the row features, return return a new row. And then so what that would create would be a row for the first element, the second element, third, fourth, etc. But then in that case, we will have black twice, right? And that's why we do distinct, to remove those distinct. And then at the end, that will give us only those encodings or the unique, those unique values for all the columns that are present, or all the values that are present in the features column, which in a way is a vector, right? As that vector representation that we created. Any questions here?
Not a question, just a quick observation to help people understand explode. It's basically like a flat map. It just it returns like what a flat map would do when you do it on an RDD.
Yeah, thank you. All right, good. Well, that's a good thing. What happens if we do this? So if we don't do this thing, we will see that twice. We'll see black twice. So it's here, and we'll see it here. Exactly. So for, yeah, that was a very good analogy. So for each element, we're breaking it into each one of the components, in this case, the tuples. Good. All right. What's next here? Next, create an RDD of key value where each feature ID category in the data frame is a key, and the values are distinct integers ranging from 0 to the number of keys -1. So that is that encoding. Let's see what we're trying to do here. Put index, collect this map. Okay, so maybe we do this by steps. So first we convert that into the RDD, and this RDD sample with some features. Yeah, this is this data frame. So what we're gonna do is extract each one of the features, or sorry, the second element of that row. No, sorry.
So the RDD will be an RDD of rows.
Yes.
So the R0 is basically return the first column of the row.
The first column of the row,
which is
will
tuple.
Yes, which would be the tuple.
Yeah, so because there's only one field in this data frame.
Exactly.
So basically we're taking the data frame from an RDD of row and we're turning it into an RDD of tuples.
Exactly. Which is this, and then this zip with index, it will zip those values with the index, which, so I think if we do this, maybe that would be a good way of seeing it. This is gonna, no, this, yeah. So probably we can do, so at this point we would have an RDD. Sure. Oh, no.
You can't show, yeah.
Okay. Yeah. So that is exactly what that what RDD is doing there, or the what that RDD contains. And then we do zip with index. It would put together the index with the tuple, and then we collect that as a map. And that's oh, now this is not gonna work. And that's what we're doing. And why you guys think that is a good thing to do in this case? Well, I guess that's in a way what we are told to do, right? But if you see, for instance, let's see, where is black? Black only appears once, right? So it is in a way automatically creating that dictionary that we did manually. Yes, that we did manually in the very first first cell, or one of the first few cells, right? We are encoding each one of the tuples into a unique number.
But zip with index, that ID that is generated is different than whatever we have in the example.
Yeah, but that doesn't matter.
That doesn't matter, yeah.
Yeah, but yeah, it is in principle different.
Yeah, let me just explain what the reason for the difference is. You did not sort your data frame or your RDD before you did the zip with index.
Right.
So if you want it to be the way you got in the sample, there needs to be an extra step here to sort the RDD, and then the zip with index will provide the index in the sorted order. Because zip with index, what it does is just goes on the entire RDD and says first record gets the number 0, second record gets the number 1, in that order. So it doesn't change the order of the RDD. If you want that number to be ordered in a certain way, you need to sort your RDD before you call the zip with index.
Right. Okay. Now, automatic creation of the dictionary. So we saw that to transform from that features vector into that one hot encoding representation, we needed the dictionary. And so it would be ideal if we could create a dictionary automatically. And that is sort of building up on this dictionary that or this sort of implementation that we did, right? So we select the column features, and we do that explode for that column. We take the distinct values and convert it to an RDD. Take the first element, zip it with index, and collect this map. So it's building up from the previous step. And so we'll look at this. So what does it contain? That's above. Right. That contains that encoding. All right. All right, so the next, I think there was a bit of confusion because this URL is not valid anymore. So apologies if people were trying to download the data set. But I'm sure if you Google that around, you were able to find the data set. At the end, I changed the lab notebook and actually placed the full URL. So hopefully you were able to get that completed. And the next section explains what is that or some process to writing or downloading that data set. So I'm going to skip over that part for now. But the idea is that you download that data set, and then you read that text file. And then so probably it will be more useful just to look at what that contains. That's all below. Take two. Oh, sure. Oh, so the data frame. No, what? What was that? Oh, display. Oh no, because I already ran the full data set, the full notebook. Okay, but yeah, that is just a matrix that would contain many features, and for each one of those features would have some value, and it would have a label, which is the first column. So the very first thing is to split the data into 3 data sets. So we somewhat did this previously when we started looking at machine learning. So you can call the function random split or the method random split on that data frame, and we split it into 3 data sets, and that's what we see here. And because we're going to be using that often, it will be a good idea to cache it. So that's what we're doing here. Okay. And I think some people might have gotten slightly different counts, and that might be just because the data set that you might end up getting was slightly different. But I doubt, yeah. Given that we have the seed, all those numbers should be the same, actually. So now this, we read this data frame as text. So we actually didn't split. Where was that? Wait. Yeah. So that's what that data frame contains. So we didn't use. So when we read that the data frame, we called read text instead of parsing the CSV directly. But there is a reason for that, because then later we're gonna define a function to go and parse it for us. So the first column is the label. So in this case, 0, meaning that there was no click, and then all the other are the features, which I don't think we know what those features actually are, but typically there will be counts or some way of representing what the user have done until that point. So here we will parse the point. So we want to ignore the first column of that, or the first element of that string. We will take all the elements starting from 1 all the way to the end. And that's what this point split does. And so once we have those features, we can enumerate those features. And what that would do would be to give a number from 1 to the number of features. And so in this case, that would be the feature ID, which will be that index that you get when you enumerate those features, and the value associated with the feature. So that will be that tuple. And that's what we will return, right? So if we look at the first element, so if we look at back here, so we have 1, 1, 5, 0. Let's see, we get the same thing here. 1, 1, 5, 0. So the first element has value 0. No, sorry. The first element would have value 1. The second element, remember that in this case, the indexing starts at 0, would have value 1. The third one, 5, and so on and so on. That's what this parsing does. Yeah.
There was a question, why is there a square bracket 0 after the first? And the answer to that is that the first returns a row, and the bracket 0 returns the first field in that row. So we're actually just looking at the first field.
Yes, right, thank you. So where do we, so it returns a row. Yeah, you can, this is the Scala, but I mean, the idea is the same. You could call, those give you the first element of the row, which is exactly what we're doing here.
I have a question. I set the same speed as yours. It's 42, but the number of training and testing is different than yours.
Yeah, I would have to look exactly what was the data set that you have on the code. But I don't think it will be very different, right?
Yeah, it's close.
It's close. So that might be something related to the data that you read. It could be that is slightly different from the data that I was reading here. So I will take it offline. I wouldn't mind looking at your notebook and figuring out if it is the same data. But if it is somewhere in the ballpark, I won't be worried about it. Yeah. And that is, of course, because there is no guarantee that we're reading the same data set. But if we were, then that should not be the case. You should have the exact same numbers. Okay. So sample data DF. Where is that one? All right. So I remember. So this is the one that we had defined previously. So if we do display that. Display sample data DF, right? So that is our initial data set. So in a way, we're gonna repeat the same process, right? That we did for this sample data frame. But then with the idea that we will use this sort of automatic process into the larger data set. So we create this parse row df that creates a label column that would be the first value in the feature column. And the feature column will be created using the parse point UDF, which we define, which we started in the previous, that we started here with this parse point function. So now we're going to create an UDF so we can apply it to the data frame. So this one converts a data frame consisting of rows of comma-separated text into labels and feature. So this data frame, we would select the column text, split that column. So this is a SQL function. This split to be imported from the SQL functions. We would split it by comma, get the first item, convert it to a double, and we're going to call that the label. And on the other side, what is going to return is, or what is going to process is the same row, or yeah, the same data frame, the same column, the column text, and then we are passing that to the parse point UDF, which is defined here, and the parse point UDF is an UDF that will take that function that we defined before, parse point, and will create an array that will contain two fields, 1 and 2, and the first one will be of long type, and the second one will be of string type. So we are assuming that we're not taking into account the actual values or the numerical values of the features themselves, but we're treating them as a string, and the long type would be for the indexing. And of course, this is one way of doing the modeling. It gets some decent results, but maybe that's not what you want to do when you're actually analyzing real data. You might want to the numerical value might have some information that you might want to include in your model. All right, and so we parse our trained data frame, and to find out the number of categories, what we will do is to, similar to what we did on that toy data frame, explode the column feature and find the distinct values for that column. Get field 1, which we define here, and we're going to call that feature number. We group by the feature number, sort, order by feature number, and then finally collect. So hopefully that is not too confusing, but the idea here is that we are finding, we're creating that, so let's see, that's all below. So this one, I don't know if this is going to be a good idea, but so we take first one. Oh, let's take the second one, which is what we did there, and the feature number. So this would be the number of times that that feature appears. Right, because that's what we're doing here with this group by. We group by this feature number, and then we sum all of them. Any questions here? Okay, no questions. Any comments are also good. If somebody did something different in their lab, this would be a good time to share your solution. If it is too different to what we've done so far, you can always share your screen, and we will all benefit from it. All right, so now we're going to start calling or using some of those helper functions that we did before. So we want to create this, the one-hot encoding dictionary from the data set. We do so by calling that function that we defined before, create one-hot encoding. And then this particular function would expect a data frame with a column features. And since the column here was named feature, we could just rename that column, and that will be enough. And we can look that in this particular case, there are 233,000 features, so quite a bit of features. So this would be equal to the number of columns in the representation, in the one-hot encoding representation. So in a way, that's what we're doing. We're unfolding all the values into different columns. So we will have a very wide matrix in this case. Any questions here? All right. Now we can start using the dictionary. And that dictionary, so one thing to note here is that we use the train data frame to create the encoding. What that means is that it could be that if we go and look into our testing and validation data set, there could be values there for which we would not have a valid entry in our dictionary, right? Because it could be that in some of those new data points, there will be no values, especially since the features or all the values, the raw values are numerical. It could be that we are missing some information there. So one alternative could be to, instead of considering the numerical values as individual, you could bin each one of those columns and then use that as your way of doing the encoding. So that would be one way to dealing with with those extra values. But certainly, when we come, whenever we come to evaluate those values for which we don't have a value present in the dictionary, we could at this point ignore them. And so, similar to what we did before, we broadcast that dictionary, and we call one UDF, for the UDF generator. Sorry, 1 second. Sorry. So then, so let me see here. Yeah, I went too far down. Double type, yeah, that we imported here is from the SQL types from Spark.
Yeah, there was a question about double type, and it's actually coming from Spark SQL type library, and that's one of the types. There is a double type.
Right. Okay.
Is there any difference, like if you use the double type, or if you cast that with double as a word?
Al, you want to answer that one? I'm not sure, actually.
Yeah, well, the double type is actually a type. You can, if you write it as a free text SQL, you can do is, cast the SQL cast as double, and it will return a double. But then you need to write it as a free text SQL, and this was done with the non-SQL way. So it's just the way you write it when you do it using those functions and not as a SQL string.
Right.
Okay, sorry, I think I got lost here. There was some distraction here in the house. Sorry about that. But yes, we were here. So the idea here would be that we will have a data frame that would have two columns: the column label and the column features, and the features would be that sparse representation of the one hot encoding. So in this case, the size of that vector is 233,000. So that is quite big. So this is a very wide matrix. But actually, if you were to look at the full data set, you would have even a much wider data frame, because we're only looking at the unique values. So later on, we could find ways to reduce this the dimension of this sparse vector. But as I say, you could in principle use binning for your features before you do the encoding, and that could help with reducing this dimensionality as well. Okay. So the next thing is to look at the frequency for the features. So in principle, all those features would appear not too many times. all the features will appear rarely, especially because they're just numerical values, and that's what we do with this plot here. So what this is saying, let's see. So the bucket size, visualize the number of times when we compute the number of the features by these counts. Right. So what we're saying is somewhat creating a histogram. So the first bucket corresponds to features that appear exactly 2 to the 0. So that will be 1 time. The second that appeared twice. The third that occurred to the 2 to the 4, and so on and so on. And the plot will show the logarithm of the bucket threshold versus the logarithm of the number of features that have counts that fall into the bucket. And that is what that plot here shows.
Yeah. So just you know, it's important to note that this is a logarithmic chart. So although it looks like a line, in action, this is like should have been. If you looked at the real value, this is an exponential line. So between 0 and 1, you have an exponential number of more that are on the 0 end, or very close to having just 1 value.
Right, exactly. That is exactly what this plot is telling you, that most features only appear only appear a few times.
Yeah.
So that's what this number is. So actually, the ones here compared to the ones here, so this will be the popular features, it's a huge difference. Yes, it's log on both sides of the spectrum. Will likely appear. So this is something that I mentioned before, that when we look at the training data set, we might find features, or we might find values that were not found when we did the encoding, when we did the dictionary for the encoding. So let me maybe break this here. So it's a little more readable. For key features, key. And then, okay. So what we have here is we're creating a sparse vector, and the size of this vector would be the number of features, which is one of the inputs to this one-hot encoding function. So this is very, very similar to what we've done so far for the small data set. And then in this case, we are sorting the dictionary. We're sorting and the used to create a sparse vector are sorted. That the function, you should ensure that the indexes used to create the sparse vector are sorted. Yes, and that's what we're doing here. We're sorting those indexes. And what this is doing, let's see. We are creating so for the dictionary, right? So these are all the values on the dictionary. Oh, I see. So we are only including the values of the key that is in the row features, and we're getting the value for which key is on, sorry, let me explain again. For all the values in the row features, we're encoding those values that are present in our dictionary. So that is the filter that would ensure that we're only encoding those values that are in the dictionary.
Well, the reason for this is quite simple. If you try to grab from the dictionary a value that's not in the dictionary, you'll get an error. and your code will explode. So that's why you have to kind of filter anything that's not in your dictionary.
Yes, exactly. And we know that there will be values that are not present in our dictionary, because our dictionary is somewhat limited. And then here we're doing exactly what we're doing is we're putting 1 if the same condition appears, right? If that feature, so if you know this part of the code for key in row features, if key is in the dictionary, in this dictionary, is the exact same here. So we are creating the same size list as the first element, and then for the second one is just 1. So we actually don't have to sort it, right? Because there will be just ones. So we're creating a bunch of indexes that are here, and then an array of ones. Okay. And I guess there will be other ways of doing this. You could, in principle, take this outside, right? And then instead of doing this sort of complicated, or this sort of the same, writing the same code twice, you could do something like, let's see if we could do it. We take this vector outside here, so something like this. V1 equals.
So there was a question, why are you sorting things? So what you're actually doing here, Armando, is you're using the sparse vector first representation, where the first list is just the list of positions, and the second list is the list of values. So you could potentially change it without the sorting, just by returning the tuple of the key, comma 1, like we did previously. Then you don't need to do the sort. It will be done by the sparse vector. And the sorting is needed here just because of the representation that you're using to create your sparse vector.
Yeah. Right, exactly. So these are our indexes, and these are our values. And that's exactly what we will place here. So we're putting ones as many times as indexes. All of this will be indexes. As many times as indexes are present. So that will be some sort of alternative solution. Then we will do return sparse vector num1 indexes. Oh, well, we have to do sorted. Something like that. Okay. Good. If anybody has another solution and want to share it, this would be a good time as well.
Yeah, somebody just posted the solution in the chat for people who are interested, which is basically what we mentioned, to use a tuple representation instead of a double vector representation.
Yeah. So I'll copy it here. Right. Good. Thank you. Okay. Then we will build a logistic regression model based on our inputs, and then for that we will call logistic regression from the PySpark ML package, and this this particular logistic regression would have different parameters that we can tune. In this case, we're not doing the tuning that we did in the previous lab, where we had a cross validation and we found the best parameter. Here, in a way, we're setting those parameters to some fixed values, but these parameters might not be the best parameters. So that would be something that if you were to run this in production, you might want to actually spend some time tuning this parameter. So the regularization parameter, the elastic net parameter, and the max number of iterations. But yes, when we define our logistic regression and then we set all the different parameters, we can then fit our model from the one hot encoding training data frame, and then from that model, we could extract the intercept and the coefficients, and then the number of coefficients would be equal to the number of features that we have. So in this case, those 230,000, and the intercept would be just one scalar, one number.
Armando, there was a question in the chat that said, why was the decision to use logistic regression instead of linear regression in this case?
Yeah. Well, you could use the linear regression as well, but in this case, what we're trying to, the sort of output that we're trying to do is binary, either 0 or 1, whether it was a click or not. So in that case, the logistic regression is a better representation for the problem, in particular because it could give you, you can interpret the output of the logistic regression as a probability. You could as well do a linear regression and then maybe define a cutoff after which it would be 1 or 0, but then the probabilistic interpretation of the logistic regression, I think that's what, particular in this case, being a binary output, would be a better model than a linear regression. But yes, you could do it in a linear regression too, but it won't be as straightforward to interpret as a logistic regression would.
Yeah, I think that they mentioned that in the videos, in the lectures, that they used because of the way that logistic regression, the number will always be between 0 and 1, and you can make sure that you put in a cutoff of 0.5 and use that as your decider, are you binary or not. I think that that was something that they covered in the lecture.
Yeah, exactly. It comes somewhat more natural. So we look at logistic sigmoid function. So this would be the output of that logistic regression would look something like this, between 0 and 1. So then, yeah, you would have that probabilistic interpretation. Well, if you have a line, which would be what the logistic regression would give you, yeah, you can quantify the distance to some sort of threshold in the middle. So if we do linear regression, let's say something like this, you could say anywhere between, in this case, anywhere past this threshold of 3 would be 1, below would be 0, but then you would have to sort of interpret that distance, while in the sigmoid function, that interpretation comes to you for free in a way, because it's directly a probability interpretation, particularly in a binary problem.
I think that in the logistic regression, in the regular regression, the linear regression, what they use is the line. So you look, are you above the line or below the line, which is what you get exactly in the representation of the logistic regression.
Exactly. And then in the linear regression, you would have to find a way to quantify that distance, right? while here it's already done for you.
Yeah.
And then, so how do we define that this was a good model or not? We use something called the log loss function. So I think I have it somewhere here in the plot. Let me see if I find it. Yeah. The log loss function is defined as minus log of p if it is the true value, and the minus log of 1 minus p if the true value is 0. So remember, in the case of linear regression, the cost function that we had was the mean square, right? So we have a cost function that when the predicted value and the true value were far apart from each other, would differ, that cost function would increase. And somewhat that is what we're trying to do here as well. We're trying to find or penalize. So when when the true value is equal 1, so meaning that in this case 1 represents that there was a click. If that's 1, then the error will be 0, right? Because it will be here. And if the true value is 1 and the predicted is somewhere close to 0, the cost function will be very high, right? So that is what that function is doing. So penalizing when penalizing a lot, or giving a high error, a high value when the true value is far from the prediction is far from the true value, and very small when the prediction is equal to the true value. And in this case, P is bounded between 0 and 1, right? Because P would be that value that we get out of the logistic regression. And then you could do the same sort of analysis for the y equals 0 case. So if we have a perfect model, right? This, when p is equal, when the true value is 1, right? This would be 0. And in the other case, when, in the second row, oh shoot. In the second row, when y is equal 0, this function will be 0 as well, right? So what this is telling us is that the smallest the value of that function for the full data set, or for our full testing, or whatever, or even in the training where you could calculate this function, the better. So the smaller, the better. So in this example, we have a column P and a column label, where label is the true value and P is that probability interpretation that we got from the logistic regression. So the next function is
Armando?
Yes.
So in this result, like if you scroll up a little bit. So yeah, in this table, so for p value of 0.99, we have a level 1, and same like 0.99, we have a level 0. How is it?
So that means in this case, the penalty will be small. In this case, the penalty will be large.
So there is a other term like penalty there?
No.
Right. The value of this cost function will be very high in this case, right? Because the true value is 0, and you're doing the logarithm of 1 minus p, y minus p will be very small. So therefore, if you look at this plot here, would be that log loss will be very high.
Mm-hmm.
Right? Versus if you're on this side, right, 1, therefore you're taking the log of p, and the log of p when p is close to 1 is very small. So
Yeah, yeah. Understand. Thank you.
Yeah. And so I think we're running out of time, so I'm going to go a little bit faster now, just so we cover a few of the other concepts. But here the idea would be to add a new column that would be log loss, and that particular column would implement the logic of the log loss. And so it would take the p-value, compare, or based on the true label, would calculate the log of p or the log of 1 minus p, depending on this label. And that's what that logic is here. I will share this notebook so you guys can compare with your own solution. The next is to do a comparison with a baseline solution. A baseline solution would be, let's look at our full data set and count the number of times that there was a click, so the number of ones, and then divide by the total number of columns. And then in a way, if you were to predict that everybody would have that value of p, that will be sort of like the baseline. So then the goal would be that any model that you do pass, any model would in principle should be able to beat that baseline, unless it's a model where it would give everybody a 1 or everybody a 0. And that's what we do here. And then so the definition of the log loss was defined on a row, per row. If you have a data frame, how do you add that, or how do you come up with that? Is that you take the mean value of the different p's, or the mean value of the different log loss functions, and that's what we do here. So we have the log loss, the fraction of ones in the data set is 0.227. So that means that of all the rows that we have, 22% of them have a 1. This is certainly very inflated, and when you go look at ad tech, the number of clicks that a particular ad would get is actually very, very small. So several orders of magnitude smaller than this. But this was inflated for this particular data set. So the next is to write a function that computes the row linear prediction from this logistic regression model and then passes the sigmoid function to return the model probabilistic prediction. And that's what we do here. So so if we have we have our input data frame, we would have labels and features. We would predict a p-value associated with each one of the rows. And we will then evaluate the model. So the typical, what you do to evaluate your model, one of the metrics to evaluate your model is called the RSC curve. And this RSC curve, given that if we look at the logistic regression sigmoid function, we look at the sigmoid function would have values somewhere between 0 and 1, and that's our output. So if you notice, say that I do my cut at 2. So what I would say is that anything that is above, in this case, somewhere around 0.86 or somewhere around there, anything past that will be considered a 1. Anything below the threshold would be considered a 0. So remember that this is a binary class or a binary problem. So that's why you could in principle move this threshold, or if you want to move the threshold all the way to -2, what that means is that anything below -2 will be assigned to the class 0. Anything past that would be assigned to the class 1. And of course, there will be times where you do misclassification, and that's in a way what this is measuring: the true positive rate and the false positive rate. So the true positive rate means that you classify something as 1 and it was in fact 1, and the false positive rate is that you classify something as 1 and was actually 0. So the perfect classifier would be one that would have 0 false positive rate, so somewhere here, and then it would have 1 true positive rate, meaning that from all the events are correctly classified, and no events were misclassified. With no events were false positives. But if we move that threshold, for each point that we move in this threshold, right? As we move closer to the right, we will have, of course, less items in the class 1, but we will have be more strict. So for each one of those thresholds, what you would do is you would find a crossing or a point in this curve. And then you would choose based on your on the sort of problem that you might be wanting to solve, whether you want to have a true positive rate that is high, so you will be somewhere here, but then you know that you will be paying by having a higher false positives, or if you want to have low false positives, then you know that your true positive rate would be smaller. So you're somewhere here, and this diagonal line would be sort of like a random, what you would do if you do a random classification.
So just in this case, Armando, I think it'd be easier for people to understand that in our case, where we want to say, hey, we want to get more a good understanding of when people will click, but we don't really care if we thought they would and they didn't. You know, it doesn't really matter for us. So the cost of false positive is really low in this case. So you just, you may lose vulnerability. So you may want to be something, you say, I'm maybe somewhere on the 0.8 where you want to say, I want to predict a high value of things, and I don't mind on the false positives. Now, if your model was predicting car crashes, right? And every time you predict a car crash, you have to stop the car and you can't drive anywhere, and you're creating a lot of delays. The cost of false positives is very high. So you want to eliminate the false positives, and you want to go, more to that range where, and you try to get closer to that as possible.
Right. Okay. So yeah, here would be the car crashes. That's my representation of a car, and this would be in this case. So yes, definitely, depending the problem, you would decide where you cut, where you do your threshold. Oh, this one. Where do you go in your curve? And then remember, for each one of those threshold points, you would have 1 point in this curve. And when you merge them together, that's what you get. And again, as Eyal mentioned, depending what kind of problem you have, you might be in different point, or you might want to be in different points of this curve. Thank you. Okay. So we still have a lot of material, and we're well past our time. But the last thing to mention is this dimensional reduction via feature hashing. So hashing is a very cool technique, and so I think I have here a plot. Yes, this one here. So hashing, what it's doing is that you have some input. So in this case, it's called keys, and then you have a function that would map these keys into buckets, and the size of the number, or the number of buckets, it will be one of parameter of your hash function. But then the idea is that it could be that there are collisions, meaning that two keys, after applying the hash function, would map to the same hash. And in a way, in this particular case, that is desired, hoping that if two things, or the ideal hash function would be that if two things hash to the same bucket, that means that, or ideally, those two things are close to each other, meaning that those two rows have similar values. So that would be the ideal case, where the collision of hashing is ideal. Not ideal case would be where the hash function just puts things that are not equal, or they're very different from each other, into the same bucket. But in a way, what you're trying to do here is reduce the number of dimension, and that's what we do here. So I think we go from 230,000 into, I think, 20,000 or so. Yes, in 32,000. So we have 232,000, and then we went and convert that into 30,000. And then, so if we were to create sort of compare the model that we get with the hash version of the data set versus the original data set, our performance would be not as good, but it gets worse, but is not terribly worse. And the reason for that is that we have a very sparse data set. So that's one of the reasons why, in this case, by reducing the dimensions by this hash trick, our model doesn't get completely out of launch. So I'll share this notebook so you guys can go into more detail, or if you have more questions, please make sure that you share them in the Slack channel and in the Google groups, and we can leave it as like that for today, given that we're well past our time. If you have any questions, or you want to go over some particular details of the last few sections, please ask now, so we can all go over it. Otherwise, we'll see actually each other in person next week, next Tuesday. Let me also get, in the meantime, the attendance sheet. Yeah. So I'm copying that to that. So there's the attendance, and also I'll put it on the Slack channel. All right. Well, thank you very much, everyone, for participating, especially to Eyal for great contributions. And we'll see each other next week then.
See you next week.
Okay, thank you. Okay, so I think there was a last question. How does hashing reduce from 330K features to 32? Yeah. So in a way, this is what's happening. You're mapping some of the keys to buckets, and you define how many buckets you have in your final space, and that is a function that you will define here. Oops. Here we define the size of that function. So if we look at this, actually.
So the model function, because you define the number of buckets, tells you that you will end up with a number between 0 and that num buckets minus 1. That's what the modulo does. So that's how you reduce a number. So think about it. If you have an integer between 1 and 100, and you say, I want the value modulo 4 of that integer, it will take all the numbers from 1 to 100 and then assign 0, 1, 2, and 3 to it, depending on how much you get after the division, right? So that's how you reduce a long number to very, very small number.
Yeah, I got a question, but when you when the two features fall in the same bucket, will you just consider as the same feature?
Now, what they did, and they answered that in the lecture, and what they said is what they do is they actually count the number of features you had in a bucket. So if you have two features falling into the same bucket, you will say your hash, the value against that hash would be 2. So you would know that there was 2 values in that bucket. You're not sure which 2 values they are, but you will know that there were 2 values that were, linked into this bucket. And that's what allowed you to you got a loss of information, but you still knew something about it. That's why you got a slightly worse result. It's because you lost some information, but because some information was still retained, you were still able to kind of figure it out.
But how your machine learning algorithm know they are the different features? Because if they treat them as same features,
it doesn't.
Yeah, you don't. Yeah.
It doesn't, but it says, let's assume that the value right now is this new sets of features. But because the hash of the large number of features to the relatively smaller number of features still retains enough information, it's enough for the machine learning algorithm to assume that and to come up with a reasonable result, even though it doesn't have the full information.
So I can assume that this kind of feature only suitable for the sparse vector if you have dense data set, so that won't be very good.
It depends on which algorithm you're doing, but again, what we're doing here is actually with bucketing. Mm-hmm. And it may make sense when you say, you know what, I'm not really interested in the actual value. So if you got 520 or 517, I'm going to consider it the same thing, right? That's basically what you're doing here. You're kind of bucketing the values, say, I'm going to use ranges instead of using individual numbers. So of course your prediction would be less accurate, but it would still be good enough.
Okay, I see. Thank you.
All right. Well, thank you, everyone. We'll see each other next week then.
See you next week.
Bye-bye.
Yeah.
Bye.
Yep.